Let's say from the define phase, your project is to reduce long and inconsistent processing times. So, how long and how inconsistent are they? That is why you need the measure phase, to measure and understand just how bad the problem is. The main focus of the measure phase is to measure the y in y equals f of x. The steps that make up the measure phase are: first, confirm the y in y equals f of x by reviewing all the outputs from the define phase. Next, describe and map the current as-is process. You do this by starting with a high-level process map, then decompose the process as needed using detailed process maps or swim lane deployment maps. Make sure that process owners and other key process stakeholders are involved. Then, you can determine what's critical to customers. In other words, develop your CTQs, or critical to quality requirements. A voice of the customer, or VOC analysis, is used to identify, prioritize, and translate customer needs into CTQs. Then you can develop a data collection plan for measuring Y. You need to identify what questions need to be answered, what data, and how much data needs to be collected, by whom, from where, and by what means. Remember, the focus is on measuring Y. The next step is to validate the measurement system to ensure integrity of data. You can conduct a measurement system analysis, or MSA. If the results show that the measurement system is not valid, then improve it first, so the data to be collected and used is indeed valid. Then, measure the baseline performance of Y. To do this, collect or measure performance data to answer the questions listed on your data collection plan. Tools you can use include sampling, sample size determination, process capability analysis, descriptive statistics, such as means and variances. You can also use various graphs and charts, including run charts, SPC charts, box plots, histograms, and bar charts or Pareto charts. Performance of the relevant Y metric, such as % on-time arrivals, processing times, and defect rates, can also be measured. Process capability, DPMO, and sigma levels are determined to establish a baseline. Last, identify key areas to focus the project. Stratify the data to provide focus on who, what, when, and where to focus the analysis in the next phase. Tools that can help you stratify data depend on the type of data. Pareto charts are very useful for stratification if the data is discrete or categorical. For example, number of complaints. Let's say if locations B and K together have the highest number of total complaints, then focus on those two locations. Box plots and dot plots are useful for stratification if the data is continuous data. For example, processing times. Let's say in a process with 5 steps, the processing times of steps 2 and 5 are high and they have the most variation. So, focus on those 2 steps. So, that's an overview of the measure phase. You can now measure the Y in Y equals f of x and understand just how long and inconsistent the processing times are. When I'm in line to check out at the grocery store, there's usually a long wait. And the wait's even more frustrating if I see grocery staff milling around and not at the vacant checkout registers. This type of workflow problem needs to be fixed, and there are a number of metrics to measure how well any process flows. To start, you can analyze the work in process, or WIP, which are all the items being processed and items in between, waiting to be processed. For example, if you are in line at the grocery store, the WIP for checkout is the total number of customers being checked out plus the number of customers standing in line waiting to be checked out. This is important because the more WIP there is, the longer the wait and the longer it takes to leave the grocery store. The rate at which customers leave the grocery store after checking out is the throughput rate. Another metric to consider is the cycle time for a process step or workstation. It's the time it takes between starts or completions of processing items. Sometimes it's known as workstation cycle time. For example, for the checkout register, the cycle time is how long it takes to complete the process of checking out each customer. Cycle time starts when the groceries are loaded onto the belt and ends when the customer leaves the checkout station. How cycle time is used depends on the context. It can be used for a machine or workstation, like the checkout register, or it can be used as cycle time for the whole production system, such as the grocery store visit. Let's say there are 4 checkout registers and an average of 10 customers pay and leave the store every 20 minutes. Then the cycle time for the grocery store is 20 divided by 10, which is 2 minutes. So customers are leaving at the rate of 1 every 2 minutes. On a per hour basis, that rate is 30 customers per hour. This is also called throughput rate. It would be great if throughput rate can keep up with the rate of customer demand so that there is no delay or buildup of WIP. The rate of customer demand is called the takt rate or takt. The origin of the word is German, meaning a musical beat or drum beat. Takt or takt rate is the drum beat of customer demand. If we convert rate to time, we get takt time, which is the time between units that customers demand. For example, for the grocery store, if the time between customers who want to check out is 1 minute, then takt time is 1 minute. And the takt rate is 1 customer per minute or 60 customers per hour. So, for the grocery store, since the cycle time is 2 minutes, then customers will have to stand in line and wait, and there will be a buildup of WIP. From a manager's perspective, if I don't want my customers to wait, then I'll want to match my grocery store cycle time to be no more than the takt time. There are a couple of things I can do. I can speed up cycle time of each checkout register, work faster, twice the speed in this case, or I will put those clerks who are milling around to work and reassign them to check out customers. I'll then increase the open checkout lines from 4 to 8. So, the next time you go to the grocery store, analyze the process flow metrics and see if the throughput rate matches the takt rate. In the measure phase of a Six Sigma project, the project team needs to collect data to measure the baseline performance of Y. Since it's not always possible to measure every item in the population, samples are collected. So you might be wondering, how do you sample? And how much do you sample? How to sample is called sampling strategy, which I covered in other Six Sigma courses. How much to sample brings us to the question, what should be the sample size? The sample size determination depends on whether the type of data to be collected is continuous or discrete. If the type of data is continuous, you'll probably need to sample from the process to estimate the mean, such as the mean processing time of invoices. Here is a sample size to estimate the mean with 95% confidence, where Z is from the normal distribution and 1.96 is the Z value for 95% confidence level, and S is the standard deviation, and D is the precision. So, how precise do you want the estimate to be? If you want the estimate to be accurate within plus minus 5 minutes, then D should equal 5 minutes. Now let's look at an example where I want to estimate the mean processing time of invoices. The standard deviation is 20 minutes. Let's say I want to be precise within plus minus 5 minutes, and I want to be 95% confident. Then the sample size N is the square of 1.96 times 20 divided by 5, which equals 61.47. Always round up to ensure we achieve the 95% confidence level. So that gives us a required sample size of 62. Now, what if the standard deviation of the process is not known? Then you can estimate from historical data, or if none is available, collect a small sample to get an estimate of the standard deviation. When the type of data is discrete or categorical data, then proportions or percentages are of interest. For example, let's take a look at proportion of defects or percent defect rate. Here is a sample size to estimate the proportion or percentage. where 1.96 is used to obtain a 95% confidence level, D is the desired precision, and P is the proportion of interest, such as error rate. For example, the error rate of invoice processing is thought by many folks in the department to be approximately 5%. I want to be precise within plus minus 1%, and I want to be 95% confident. So here is the sample size calculation. Always round up. These are sample size formulas. The project team now knows how much data to collect to measure the baseline performance of Y. When I'm on a fitness and weight loss program, I want to know that I can trust my weight measurements, regardless of whether I weigh myself at home or have the nurse do it at my doctor's office or by officials at the Olympics. The measurement system must be valid and include everything: the instrument, the operator, the collection procedures to measure and record data. In Six Sigma projects, we also use a technique called the Measurement System Analysis, or MSA for short. MSA is done early during the measure phase so that any data to be collected or used is valid. Let's take a look at using MSA for continuous data. When measurements are made, the variation that's observed consists of two major components: the actual part-to-part variation and the measurement system variation or error. Ideally, the measurement system variation should be zero so that the observed equals the actuals. But there's always going to be some measurement system variation. Hopefully, it's a minimal percentage compared to the total variance that's observed. The rule of thumb is less than 10%. Now, let's look at the components of variation. Measurement system variation consists of variation due to gauges, the measuring equipment, and variation due to operators, the people doing the measuring. Measurement system variation or errors can be location-related or spread-related. Location-related variations are bias, stability, and linearity, while spread-related variations are repeatability and reproducibility. Let's explore these ideas a bit more, first starting with location-related variations. Bias is the difference between the observed mean or average of measurements and the true actual or reference value. For example, if a bathroom scale is not centered on 0 when there is no one standing on it, then there is bias. Bias is easily corrected by calibration. Next is stability, which refers to the measurements being stable and not drifting over time and not changing over time. There is also linearity, which is the difference in bias throughout the operating range of a gauge. A good example is your car fuel gauge. The error rate is not constant over the range of the gauge. Most of us have experienced this difference in error when the gas level is shown as full, in the middle, and when the tank's empty. Now let's move on to spread-related variances. To be repeatable means that if I weigh myself twice or even 3 times on the same scale, I should get the same readings. Repeatability measures the ability of the measurement system to be consistent when the same item is measured again under the same conditions and by the same person. Now, to be reproducible, my weight at home should be the same as when the nurse weighs me at the doctor's office. Reproducibility measures the ability of the measurement system to be consistent across individuals. Now you're aware of the key terms used in measurement system analysis for continuous data. In the next video, we'll discuss how to carry out a MSA study. Let's now look at how to conduct a measurement system analysis, or MSA, for continuous data using Minitab, a popular statistical software used by black belts and green belts. Before jumping in, let's discuss some key points in planning for an MSA study. First, you need to determine the number of appraisers, sample parts, and repeat readings or trials in advance. Next, select your appraisers from those who normally operate the instruments. Follow that by selecting sample parts from the process and ensuring that the values represent the entire operating range. Be aware that the number of parts and number of trials should reflect the criticality of the measurement. More critical measurements require more trials and parts. Also, the measurement method and tools should be the same as those used in the production process. Make sure the parts are numbered in advance. And measurements should be made in a random order. Appraisers should not know which part is being measured. Let's illustrate this with an example. To conduct this MSA study, we selected a sample of 10 parts that represent the entire range of process variation. The parts are numbered 1 to 10. We used 3 appraisers, Larry, Curly, and Mo. The MSA study was also designed to have 2 rounds of trials or replicates. A gauge R&R worksheet was then created in Minitab. Each appraiser measured all of the 10 numbered parts given in random order by the MSA facilitator by following the run order in Minitab. The appraisers did not know which numbered part is which. Each measurement by the appraiser was recorded by the facilitator. Now let's go through this example step by step. You can follow the example by using the Minitab worksheet in the exercise files. These are the results of your LCM.mtw MSA study. To analyze it, go to Stat, Quality Tools, Gauge Study, and do a select the crossed gauge R&R study. And key in the respective columns. We're using the ANOVA method. For options, let's specify the specifications, upper and lower spec for this. 0.5 for the lower specification and 10.5 for upper specification for the product. Okay, and let's go. Here we have the printout of the various charts for the analysis. The main one I look at is this very first one with the color bars. Essentially, is the percent contribution of the variation by the various components. Ideally, if you had perfect reproducibility and perfect repeatability, all the variation will be due to the part to part. That would be 100%. But because we have some measurement error, they show up as the R&R here, and these 2 components add up to the gauge R&R. And over on the right, you have the 3 charts here. If you had perfect R&R, the lines will overlap across the 3 operators. The box plots will be identical. And this line here connecting the means will be horizontal. And finally, over here, for the parts operator interaction, if there was perfect R&R, you have overlapping lines. If there is dispersion, there is some R&R problem. That being said, we have the printout in the session window. And here we have the ANOVA table, the gauge R&R, percent contributions. The good news is our total gauge R&R percent contribution only amount to 2.98%. That's less than 3%. Ideally, anything below 10% is great. So our majority of the variation is due to the part-to-part at 97%. That's very good news. Another piece of good news we have here is the number of distinct categories being 8. Anything higher than 5 is good news. This is a good measurement system and it's valid overall. Another useful chart I'd like to see is how the parts are measured by the various operators and see if they are consistent with themselves and with each other. Graphically, it's called a gauge run chart. Let's go to the Stat, Quality Tools, Gauge Study, Gauge Run Chart. Let's specify the columns. And OK. And there you have it. Let's make it bigger. You can see the 10 parts being measured twice by each of the 3 operators with the different colors, as you can see on the legend here. If you had perfect agreement, you would have horizontal alignment. So in part number 2, Larry was consistent between the first and second trial, and so was Curly, and so was Mo. And all 3 of them are lined up horizontally, which means they provided the same reading for the same part number 2. That's fantastic for part number 2. For part number 9, Mr. Curly over here is not consistent with himself between the first and second trial. And you can see the three operators are not in alignment in part number 9. It's a very nice visual chart to see what's going on, to pinpoint where the inconsistencies are, so that you can train them on it and provide the correct training and procedures to rectify and improve the measurement system even further. So that's that for MSA with continuous data. Sometimes your projects may have to deal with discrete or categorical data. For instance, say a defect rate is 75%. Or what if reason code B accounts for 80% of all calls to customer service? Before using this data, a measurement system analysis or MSA for attributes must be done to ensure the data from the evaluation of attributes is valid. The assessment of attributes may result in a pass-fail on an inspection, or it could be the classification of incoming calls by customer service reps as to whether it's reason code A, B, C, or D. This type of MSA is called attribute agreement analysis. In attribute agreement analysis, you want to evaluate 3 calculations. First, the percent agreement between appraisers, which measures reproducibility. Next, the percent agreement within appraisers, which measures repeatability. And the percent agreement with the expert or standard. To conduct an attribute agreement analysis, there must be multiple items to be evaluated. There also needs to be at least 2 trials so repeatability can be assessed, and at least 2 appraisers to evaluate reproducibility. An expert also needs to evaluate the items to provide the correct answer or standard, which is based on the established evaluation criteria. When planning for an MSA study, here are some important things to remember. First, determine the number of appraisers, the number of sample parts, and the number of repeat readings or trials. Next, select appraisers from the normal assessment team. Then, make sure the sample items are numbered in advance. Also, assessments should be made in a random order. Appraisers should not know which part is being measured. Now, let's take a look at how to conduct attribute agreement analysis using Minitab. Download the file attribute.msa.mtw from your exercise files. Here we have the worksheet whereby we have 3 appraisers, Mary, Tom, and James, evaluating 15 sample parts with 2 trials. And the outcome of the assessment is a pass or a fail. Here we have the columns for the run order of the MSA study, the actual samples by number, the appraisers, the result of the appraisal by each of them, and the standards by the expert or the correct answer for that particular part. To analyze this, let's go to Stat at the top, Quality Tools, Attribute Agreement Analysis, and we have this dialog box where we specify the various columns. The attributes are in assessments, samples in samples, and the appraisers are appraisers. Since we have the correct answer or the standard done by the expert, so let's specify the correct answer or standard at the bottom box here. And it's double click on standards. There we have it. Click OK. The first thing we see is a very nice chart showing the assessment agreement. On the left side, you have within appraisers, and the right side, you have the appraiser versus standard. The blue dots are the actual mean values, and the red lines indicate the confidence intervals for each of these appraisers. As you can see here, Mary has done a great job above 90%. Tom and James are below 90%. On the right-hand side, similarly, Tom is not as good as the rest at about 80%, and Mary is still the best with respect to agreement with the correct answer. The details of this chart can be seen in the session window output. Let's go there next. Make this a little bigger. And let's go to the top. Here we have it. So the numbers are shown here for Mary, Tom, and James as far as percent agreement. And below that, you have the kappa values. Let me explain what kappa is. Kappa shows the level of agreement. The stronger the agreement, the higher the value of kappa. If kappa equals 1, there is perfect agreement. If kappa equals 0, the agreement is the same as it would be by chance. So we want a high kappa value. Here are the guidelines. Between 0.9 and 1.0, that is indicative of an excellent measurement system. Between 0.7 and 0.89, while not excellent, it is still a capable measurement system. Below 0.7, it needs improvement. Below 0.5, you need help big time. So that has to be improved before even thinking about using this measurement system if it's below 0.5. The next report shows how each appraiser agrees with the standard. The details can be seen in the lower half of this report, whereby the appraiser rated as a pass when the standard says it's a fail, or when the appraiser rates it as a fail when it should be a pass according to the standard. And over here, the number mixed is when the appraiser could not agree with himself or herself between the first and second trials. Next, we have the between appraisers showing the agreement among the three appraisers. And we can see the big number here at 73.33%. That is not good. You want that number to be 90% or higher. Otherwise, the measurement system is not valid. In this case, it's not. It requires improvement. And that's reflected in the kappa values below. Finally, you have all appraisers versus standard. Once again, it takes all three folks against the standard. Once again, at 73.3%, it is not good. We have to improve the measurement system. So from an earlier chart that we saw, it looks like Mary does an excellent job. The people who require more training are Tom and James. So that's MSA for attribute data. Imagine a house with a garage. Perhaps it's yours. Is your car capable of entering the garage safely without hitting either side of the garage doorway? Yes. Why? Well, I know it's obvious, but it's because the width of the doorway is wider than the width of the car. Now imagine your car is a process, and the width of your car represents a natural process spread or variation. Looking at the garage doorway, visualize that the lower and upper specification limits are the left and right edges of the doorway. The width of the car, or the process spread, in our analogy, can fit in because it is narrower than the specification width. But what if the process was as wide as a school bus? Then it wouldn't be capable of going through the doorway. How capable the car, the bus, or the process is in meeting the specification width is called potential process capability, or CP. For a normal curve, the process spread is 6 standard deviations, 3 to the left and 3 to the right side of the mean. When CP is equal to or greater than 1, we say that the process is potentially capable of meeting specifications. As shown here, CP is greater than 1. CP measures the best case process capability that can be achieved, assuming the process mean is always on target. As shown here, the process spread is wider than the specification width, so CP is less than 1. But your aim may be off target. Let's say the middle of your car or the mean of the process is not always centered in the middle of the doorway or middle of the specification width. Sometimes the aim is off-center, veering to the left or to the right. Like your car, processes shift too. To account for actual performance, there is another index called the Actual Process Capability Index, or CPK. It factors in where the process mean is in relation to the upper and lower specification limits, respectively. How capable the process is in not exceeding the upper specification limit, USL, is called CP upper. CP upper is the distance between the upper specification limit, USL, and the process mean, divided by half the process spread, which is 3 standard deviations. How capable the process is in not going below the lower specification limit, LSL, is called CP lower. CP lower is the distance between the process mean and the lower specification limit, LSL, divided by half the process spread, which is 3 standard deviations. CPK is the minimum of CP upper and CP lower, whichever is smaller. Mathematically, it is shown here, where X bar is the process mean, USL and LSL are the upper and lower specification limits, and 3S is 3 standard deviations, which is half the process spread. When CPK is equal to or greater than 1, the process is capable. CPK shows the actual location of the process spread in relation to the upper and lower specs. CPK is never greater than a CP. The best case scenario is CPK equals CP when the process mean is centered in the middle of the specs width. If CPK equals 2, the specification width is twice the process spread. Since the process spread is always 6 standard deviations wide, then the specification width has to be 12 standard deviations. The distance between the process mean to either specification limit is 6 standard deviations. That makes it a 6 sigma process. If you recall from Six Sigma fundamentals, sigma level is the number of standard deviations between the process mean and the nearest specification limit. Generally, to convert CPK to a sigma level, simply multiply it by 3. Using this formula, with a CPK equals 2, the sigma level is 3 times 2, which is 6. Therefore, a CPK of 2 is a 6 sigma level of performance. Remember, the most commonly used process capability indices are CP and CPK. CP measures potential process capability, and CPK measures actual process capability. And the sigma level is 3 times CPK. Using these process capability indices enable you to measure the location and the spread of the process in relation to the specification limits. The analyze phase in Six Sigma is what makes DMAIC projects so powerful. During this phase, the purpose is to determine which axes are the key factors that impact the problem Y. In short, which key axes belong in Y equals f of x. Remember, here are the 5 steps in the analyze phase. First, generate a list of potential axes that impact Y. Next, organize the potential axes. Then, compile a shortlist and select the likely key axes. Next, develop a data collection plan for the analysis. And last, you need to prove the key axis in Y equals f of x. So let's build on what was covered in the Greenbelt training by focusing on step 5. In this chapter, we'll explore the statistical tools needed to prove or disprove the key axis. We'll go beyond the why, when, and what, focusing on why use a tool, when to use it, and what the results mean. We'll build on those elements and also include the how to carry out the different hypothesis tests, and how to interpret the statistical outputs, including how to select the correct test using a hypothesis testing roadmap, then how to test for normality, and how to use confidence intervals. We'll also determine the sample size needed for the tests, and how to compare means, medians, and variances. We'll also look at chi-square tests of independence, tests for correlation, and we'll run a linear regression and multiple regression to establish Y equals f of x. This chapter helps a black belt learn how to conduct hypothesis testing to prove or disprove the key axes that impact Y and establish the Y equals f of x equation. Let's say your project has selected theories to be tested. For each theory, you might be wondering which statistical test should be used to prove or disprove the axis. To help with this, let's take a look at a roadmap to guide you through the maze of options that can be used during hypothesis testing. Remember, the types of data of the X and the Y drive the selection of the statistical test. And data types can either be continuous or discrete. For example, in testing for differences in mean processing times of different offices, Y is the processing time and it is continuous data. X is the office A, B, C, and D, and X is discrete or categorical data. Remember that categorical is a more contemporary term than discrete data. Here's a roadmap or matrix that can guide you in selecting the correct statistical test. You can also download this from the exercise files for future reference. Let's start in the top left quadrant. If the Y is continuous and the X is discrete, graphs such as histograms, box plots, and dot plots are useful in showing both the location and the spread in the data. Statistical tools that are applicable include normality tests, t-tests, and ANOVA, and variance tests such as those using the chi-square method and Bartlett's test. If data is non-normal, use the Bonnet method and Levene's tests for testing variances. And instead of testing for means, test for medians using non-parametric methods such as the one-sample Wilcoxon, the Mann-Whitney, and the Kruskal-Wallis. Now let's consider another example. Is there a relationship between driving speed and stopping distance? To determine the test to use, let's look at the top right quadrant. If Y is continuous and X is continuous, graphs such as scatter plots and fitted line plots can be used with statistical tools such as correlation, linear regression, and multiple regression. Here's another example. Say Y is the number or proportion of successful surgeries, and X is the hospital, A, B, C, or D. In this example, Y is discrete data, and X, the hospital, is discrete or categorical data. So in the lower left quadrant, if Y is discrete and X is discrete, graphs such as Pareto charts are very useful. Proportions can be tested using the proportions test, and count data can be tested for independence using the chi-square contingency tables test. In the lower right quadrant, if Y is discrete and X is continuous, logistic regression can be used. For example, let's say Y is yes or no on having a heart attack, and X is the milligrams of aspirin taken. Studies like this take a long time because logistic regression requires a lot of data, so it's seldom used in Six Sigma projects. I hope this roadmap is helpful when selecting the right statistical test for your analyze phase. When you run a hypothesis test, there's always a chance of committing a type 2 error, which is not rejecting the null hypothesis when it is in fact false. The probability of that happening is called beta. You want beta to be as small as possible. The hypothesis test should have sufficient power to be able to reject the null hypothesis when it is false. The power of a test is the probability of correctly rejecting the null hypothesis when it's in fact false. The higher the power, the smaller the beta. To be exact, power equals 1 minus beta. So, what affects power? It depends on the test, but power is largely dependent on sample size, the variation in the data, and since power is the ability to detect a difference when there is one, the smaller the difference to be detected, the higher the power that's needed. For example, to be able to detect and prove a difference of 2 minutes between the mean processing times of two groups requires a more powerful test than one which needs to detect a difference of 10 minutes. Let's look at a two-sample t-test using Minitab. To start, download the worksheet meansdata.mtw from the exercise files and open the worksheet. Here we have the outputs of 4 groups A, B, C, and D. Before the two-sample t-test, let's check for normality of data. There are a couple of ways to do that in Minitab. The first way is to go up to Stat, Basic Stats, Normality Test. The trouble with this approach is that you have to do it 4 times over because you have 4 groups. So let's skip this and choose the alternate approach, which is graph, probability plot, choose multiple because we have multiple columns for the 4 groups. And let's select A through D and choose OK. Here we have the plots as well as the Anderson-Darling tests and the p-values that go with it. Remember, for this test, a high p-value higher than 0.05 means the data is normal. As you can see here, all the p-values are higher than 0.05. Therefore, all 4 groups have normal data. This is supported by the chart, which shows that the dots are pretty close to the respective lines. If it was perfectly normal, the dots will be on the lines. Let's check out the stats for this group of data. Go up to Stat, Basic Stats, Display Descriptive Stats. Select the 4 groups. OK. Here we have the sample size n equals 100, the mean values, standard deviation, and the various quartiles. So if we were to run a 2-sample t-test, let's say A versus B, or B versus C, or A versus C, what would the power be with a sample size of 100? So we can do that with Minitab. Minitab has a nice feature called power and sample size to help you determine the power for various sample sizes or the sample size you need for various powers. Go up to Stat, Power and Sample Size. Here you see the various tests involved for hypothesis testing as well as for DOE. In our case here, we're interested in the 2-sample t-test. In this dialog box, there are 3 entries. The way this works with Minitab is you provide any 2 and Minitab provides the third. So in our example, let's say if I'm interested in finding out what the sample size is for a particular power, I can key in 0.90 space 0.95. So my question to Minitab is, what would the sample size be for these 2 power levels? Let's say I want to detect a difference of 1 in the 2-sample t-test. And let's say my standard deviation is 2. What sample size do I need to run this 2-sample t-test? Under Options, you can specify the hypothesis involved. Let's choose a not equal for the alternate at the alpha level of 0.05. So that's fine. And click OK. Here we have the power curve showing the difference that can be detected and the various power levels. So for the 2-sample t-test, to detect a difference of close to 0, the power levels are very low for these sample sizes, and it's close to 90% for detecting a difference of 1, which is what we specified earlier. So the sample size of 86 is for 90% power, and 105 sample size is for 95% power. The details can be seen here in the session window. As you can see, 2-sample t-tests, the alternate hypothesis, what must you detect, what the standard deviation is, and you have the target power which you specified at 90 and 95. Minitab came back with 86 and 105 respectively, where the actual power is actually a little higher than your targets, which is good. That's what you want. Now, if we were to run a 2-sample t-test using this data that we have, as you can see, this is our data set earlier for the stats. What would the power be with an n sample size of 100? So let's go back to the menu again. We can do a Control E to get the latest previous menu. So let's say our sample size is 100, which is what it is. We want to detect a difference of 1, and we have no clue what the power is, so delete that. Provide 2, Minitab provides a third. And let's say our standard deviation is, for the sake of argument, rounded out to 2. What do we have? We can click OK here. And here we find that the power is very high. Let's go to the session window. And we see that with a 100 sample size, we achieve a 94% power. That's very good. For the sake of illustration, let's check this out. Control E to get to the previous dialog. From the printout earlier, we know that some of these standard deviations are as high as 4. Let's click 4. Let's see what power we get with this sample size to detect a difference of 1. Very low power. In the printout, we see that the power is only 42%. So our sample size is too small to be powerful enough to detect a difference of 1. In this example, we have to increase sample size or accept a lower power. As a rule, you want power to be 90% or higher, otherwise your test is not valid. So that's power and sample size. Let's say you're interested in determining the mean height of the employees in your company, but there are 500 employees. It's not practical to measure every one of them. So you take a sample of 20 employees and find that the sample mean is 69.87 inches. How confident are you in saying that the population mean is exactly 69.87 inches? You probably have a 0% confidence level. Now, how confident will you be in saying that an interval of 0 to 100 inches includes the population mean? Now you're probably 100% confident. But having a 100% confidence level with such a wide interval is not useful. That interval is called the confidence interval, which is a statistically calculated range of values that contains a population parameter, such as the mean, with a certain level of confidence. It's most commonly set at 95%. Here is a graphical summary of the sample data for mean height using Minitab. You can see the sample size is 20, along with all the summary statistics. The sample mean is 69.871. The 95% confidence interval for the mean is 69.036 to 70.705 inches. Confidence intervals can also be established for the median and standard deviation, as you can see on this graphical summary. The most commonly used confidence level is 95%, although, depending on application and industry needs, sometimes 90% or 99% is used. Now let's say additional groups of 20 employees were measured. And for the sake of illustration, we repeated the process for 25 groups. Here's an interval plot showing the 95% confidence intervals for the population mean. The sample means are the blue dots. The true population mean is actually 70 inches, as indicated here with the red line. Notice that most of the intervals include the population mean of 70 inches. Maybe 1 or 2 does not. This isn't a surprise because if we had 100 groups, we will have 100 sample means and 100 confidence intervals. Since the confidence level is 95%, chances are 95 of them will include the population mean and 5 will not. Now, here are the interval plots of groups with a smaller sample size of 10 employees each. Notice that the 95% confidence intervals are wider. This isn't a surprise because as sample size gets smaller, it becomes less accurate and we get wider intervals. In hypothesis testing, confidence intervals are often used to visually see if there are differences between groups. If confidence intervals do not overlap, we can be confident in saying that the groups are different regarding the value of that population parameter. Let's say you want to conduct hypothesis testing to prove differences in the population means or variances between groups or against a target value. That output could be dimensions, processing times, or any characteristic that's continuous data. Many statistical tests require that continuous data follow a normal distribution, commonly known as the bell-shaped curve. But not all continuous data are normally distributed. Testing for normality is essential because some tests require normal data. Otherwise, they will fail to work and give you the wrong conclusions. In another video, we look at a hypothesis testing roadmap to show the correct test to use. Let's look at the top left quadrant of that matrix. For example, when comparing means, the one-sample t-test, the two-sample t-test, and ANOVA or analysis of variance all assume the use of normal data. When comparing variances, Butler's test for equal variances also assumes normal data. If data is non-normal, then non-parametric tests such as the one-sample Wilcoxon test, the Mann-Whitney test, and the Kruskal-Wallis test are used, where medians are compared. These non-parametric tests are used in lieu of the t-tests and ANOVA. To compare variances for non-normal data, Levene's test is used instead of Bartlett's test. So, when running a normality test, you have to do a test for each data set. Here are the hypotheses for testing for normality. The null hypothesis is data is normally distributed. In other words, it follows or approximately follows a normal distribution. The alternate hypothesis is that the data does not follow a normal distribution. In other words, it is significantly non-normal. The most commonly used and preferred normality test is the Anderson-Darling test. Let's say these are some of the delivery times from 4 pizza restaurants, A, B, C, and D. The normal probability plots show the following. In this graph, if the data for each restaurant was perfectly normal, the data points will all lie exactly on the normal probability plot lines. Now here are the test results for the Anderson-Darling test. Since the p-values are higher than the alpha of 0.05, we fail to reject the null hypothesis for each of the 4 restaurants. So the conclusion is the data are normal. Now that we know the data are normal, the correct statistical test can be selected and used. What if you want to compare outputs of 4 groups? The output is continuous data for all 4, and it could be dimensions, processing times, or any characteristic that is continuous, such as the time it takes for me to complete a triathlon or deliver pizza. If the theories you want to test are about the variability or consistency of performance, then you want to compare their standard deviations and variances. Let's take a look at an example of this using Minitab. Download and open the file variancetestdata.mtw. This can be found in the exercise files. Here we have the output of 4 groups. These are all continuous data. They could be processing times, delivery times. And you want to test the consistency of performance against a target standard deviation or variance, say a target variance of 9.0. So the theory to be tested is that the groups are more consistent than this target variance of 9.0. So we need to run a one-sample test on each of these groups. To do that, go up to Stat, Basic Stats, One Variance Test. And we have the 4 groups being selected. And our hypothesis test to be performed is against a variance of 9.0. Select Options to specify the alternate test. Given our theory, we have to choose less than hypothesized variance for the alternative. Alpha is 0.05, which is 95% confidence level. And let's run the test. Make this slightly bigger. And we have the hypothesis test, HOHA. If the data is normal, we look at the chi-square method. If we do not know, choose the Bonnet method. And these are the sample variances from the samples. Notice that A and D are pretty close. But the confidence intervals from those tests show that the only one that is less than 9.0 is A, whose upper bound is 8.29 under both the chi-square and the Bonnet. So it looks like A is the only one that meets the target variance of less than 9.0. This is confirmed by the p-values. For A, it is less than 0.05. For the rest, it is more. So less than 0.05, reject the null. Therefore, A is the only one that has a variance of less than 9. What if we are interested in testing the variances between A versus D, since they're so close? Are they different? To do that, run a 2-sample variance test. Go up to Stat, Basic Stats, 2 variances. Since we have 2 columns, specify them as such. Sample 1 being A, sample 2 being D. For the options, we're trying to compare variances, so select that. Confidence level is fine. The hypothesized ratio is 1. That's good because we're checking for equality. And the alternate is not equal to. Okay? and select OK. And this graph shows the 95% confidence intervals for that ratio of the two variances. They both overlap. This is confirmed by the p-values for the Bonet's test and Levene's test, both of which are higher than 0.05. Therefore, you cannot reject the null hypothesis, confirming our visual view of the overlap. The variances are not different. So there you have it, two-sample variance test. If you want to test for equal variances, then go up to Stat, ANOVA, Test for equal variances. We have separate columns. Select all four. So we're testing all four variances to see if any one is different. Here we have it. Some are different, some are overlapping. The p-value of 0.00, which is less than 0.05, means that we have to reject the null hypothesis. The null hypothesis in a variance test is that variances are equal. Therefore, rejecting that means that the variances are not equal. So for example, the variance of B and C, while they're the same or similar, is quite different from the variance of A or D because they don't overlap. And the p-value confirms that. They are not all equal. If they were all equal, all the CIs will overlap. The test for equal variances is critical and required before running the ANOVA test, because that's a key assumption of ANOVA is equal variances in addition to normality. So this will be useful for you when you do the ANOVA test. There you have it, test for equal variances. During the analyze phase, some theories may include testing for differences in population means. For instance, are average pizza delivery times different between restaurants? And do they meet the promised delivery time of 30 minutes or less? Whether it's comparing the performance of one group to a target value or comparing the performance of two groups, the one-sample t-test and a two-sample t-test can be used to evaluate sample data to make inferences about the population means. Let's look at these using Minitab. To get started, download the file meansdata.mtw from the exercise files and then open it. Here we have outputs from four groups. These are delivery times or processing times of four locations A, B, C, and D. Let's say we're interested in testing whether the mean performance of A is equal to 20 minutes or not. So we need to run a one-sample t-test. But before we do that, we must check for normality of data. Otherwise, the one-sample t does not work. For normality tests, go up to Stat, Basic Stats, Normality Test, select A. Anderson-Darling test is good. That's a very useful test. And here we have it. If the data was perfectly normal, all the blue dots will be on the red line. It's almost there. This is confirmed by the p-value of 0.975. In a normality test, the null hypothesis is data is normal. So with a high p-value of 0.975, which is greater than 0.05, we fail to reject the null. Therefore, the data is normal. That's good news. So let's proceed to the one-sample t-test. Go up to the Stat menu and select Basic Stats and choose one-sample t. Select A as the data column you want to perform a test against the hypothesized mean of 20. Select Options in order to specify the alternate hypothesis, which is fine over here. It is not equal to, and to specify a confidence level that you desire. In this case, 95.0 is perfect for us. Click OK. And we can select graphs. I like the individual value plot and box plot. And let's go. Okay, here we have the box plot showing the hypothesized mean in the red target symbol and the confidence interval for the data in terms of the population mean. So we see that the confidence interval does not overlap with the hypothesized mean. This means that it is different from 20. Similarly, for the confidence interval over here, for the individual value plot, it does not overlap with the red dot. To confirm that, let's look at the session window with the detailed printout. Here we have the one sample t-test on A. We have the mean, sample mean, and then we have the 95% confidence interval for the population mean, which if you see here, 18.7 all the way up to 19.2 does not overlap with 20. The p-value on the t-test confirms it. A p-value of 0.000, which is much less than 0.05, our alpha, means that we reject the null hypothesis. When the p is low, reject the null. So we can conclude that the A's population mean is not equal to 20. That's the one sample t-test. Now, what if you're interested in running the two sample t-tests? For example, A versus B. We can do that too. To do the two sample t-test, go up to the stat menu, basic stats, two sample t-test, and our columns are separate. So choose sample 1 is A, sample 2 is B. The options, we can specify confidence level and the hypothesized difference. If we are testing for non-equality or equality, then the difference should be 0. Sometimes if you are in the bragging mood, say, hey, my office A is better than your office B by 20 minutes. I can put 20 in here as the hypothesized mean. But if you're testing for equality or not, then it will be a 0. And in our case here, we chose not equal to. And if you have no clue on the equal variances between the two groups, do not check this. If you know for sure with a test, then you can check it. In the meantime, let's leave this blank. Graphs. Let's choose individual value plot and box plot, no extra charge, and click OK. Here are the box plots. Minitab provides an extra feature showing the means as the target symbols, and if they were identical, it will be a horizontal line. Similarly, here we have the individual value plot showing the means as the blue dots. To be accurate, look at the session window. Make this slightly bigger. And we have the two sample t-tests showing the sample means and showing the confidence interval on the difference. Since the confidence interval for the difference in the two means does not cross the 0 mark, this means that it is different from 0. This is confirmed by the t-test and the p-value. A p-value of 0.009 is less than 0.05. When the p is low, reject the null. So reject the null, we have a difference in the means of those two groups. There you have it, the two sample t-test. What if you want to test for differences in population means across multiple groups? It may be processing times, dimensions, or any characteristic that is continuous data, such as my 100-meter sprint compared to champions like Usain Bolt. When comparing the performance of two or more groups, the ANOVA test uses sample data to evaluate and make inferences on whether population means are statistically different or not. And if they are different, pairwise comparisons can be made to determine which ones are different. Let's run ANOVA using Minitab. To get started, download the file anovadata.mtw from the exercise files and open it. Here we have 4 groups, continuous data, and we're interested in testing the means across the 4 groups, essentially running an ANOVA test. But before we do that, check for normality and equal variances. For normality, go up to Graphs, Probability Plot. Since we have multiple groups, choose Multiple, and highlight those 4, select and run the test. Looking at the p-values, they are all high. A high p-value for normality test means the data is normal. Good news. Next, let's test for equal variances. To do that, go up to the Stat menu, ANOVA, Test for equal variances. Our data is in 4 columns, so let's select that. Select those 4, and run the test. Here we have the equal variance test. As you can see, the confidence intervals overlap. That means that they're not all different. The p-values are high, and they confirm that the variances are not different. A high p-value we fail to reject the null. The null is that they are equal variances. So those two key assumptions have been satisfied. We can now run the ANOVA test. To do that, go up to the Stat menu, select ANOVA. Since it's one factor, we choose one way. Our data is organized in 4 columns. So we select all 4. For comparisons, let's choose the 2 key. In case we need to do a pairwise comparison, we can run a 2 key test. Here we have the interval plot showing the 95% confidence intervals for the population means of these 4 groups. They don't all overlap. In fact, C looks different from the rest of the pack. And the 2 key test shows that C is different from the rest. So what this does is to compare in pairs, 2 at a time, if there are any differences against the 0 mark. So as you can see here, it's a big difference between A and C, difference between C and B, difference between C and D. It looks like C is the one that's different from the rest of the pack, which is confirmed by the previous graph. Let's look at the session window. We have the ANOVA, and we have the p-value from the ANOVA table of 0.000, which is less than 0.05, so it is significant. Therefore, we reject the null hypothesis, and the null was equal means. Reject that, therefore at least one mean is different. From our graphs, we know it is C. That was confirmed by the interval plots as well as the 2 key test. And the results of the 2 key test are shown here, where C belongs to one group, whereas the other 3 belong to a different group. Therefore, C is the one that's different. So there you have it, the ANOVA test. If your grandmother needs to undergo a particular surgery and there are 4 hospitals in the local area, does it matter which hospital performs the surgery? Before you decide, you need to determine if the outcome is independent of or dependent on the choice of hospital. To do this, let's take a look at the chi-square test using contingency tables. So let's say these are the 4 hospitals that perform the particular surgery that grandma needs. This is the most recent data from the past 12 months. The possible outcomes are full recovery, partial recovery, and death. Based on this data, is the outcome independent of hospital, or is the outcome dependent on hospital? The appropriate hypothesis test for this is the chi-square test for association, also called the test for independence. In general, the null hypothesis is outcome Y is independent of factor X. And the alternate is outcome Y is not independent. In other words, it is dependent on factor X. In our example, the surgical outcome is independent of hospital. In other words, the choice of hospital has no effect on surgical outcome. The alternate hypothesis is the surgical outcome is dependent on hospital. So, choice of hospital has an effect on surgical outcomes. Now, what would the count be if outcomes had no association with hospitals? This is called the expected count. The expected count is just that. It's what you would expect if surgical outcomes were independent of hospital. So, the count for that outcome represents the same proportion of surgeries performed, regardless of hospital. Here is the formula for expected count with the results in the contingency table. The test for independence is based on the chi-square statistic and the chi-square distribution. The chi-square formula is shown here along with the chi-square distribution curve. Minitab will calculate the chi-square statistic for you, and the corresponding p-value will be displayed in your output. To calculate the chi-square statistic for our hospital example, we add up all the chi-square contributions from each cell to obtain the chi-square statistic for the test. With this in mind, let's run the chi-square test using Minitab. To get started, download from the exercise files independencetestdata.mtw and open it. Here we have the 4 hospitals and the 3 potential outcomes for the surgery. To run the chi-square tables test, let's go up to Stat, Tables, chi-square test for association, and our data is organized in a two-way table. So let's specify that with the 4 hospitals. Select those. And let's label the rows and columns for our printout. The rows are the outcomes, and the columns are the hospital. So let's type in hospital, so it's easier for us to read later. For the stats, let's select the, of course, chi-square test, the observed count. We don't need a marginal count. Expected counts, as well as the chi-square contribution in each cell. Okay. And okay. Let's make this bigger. In the session window, we can see the big printout. Here we have 3 entries in each cell. The top entry is the observed count, actual. The second entry is the expected count, as we discussed earlier. And the 1.5, or the third entry here, is the chi-square contribution from that cell. And Minitab calculates this for us. And the chi-square statistic is at the bottom here, 23.648, which is a summation of all the chi-square contributions. The test was run, and the p-value is 0.001, both for the Pearson chi-square as well as for the likelihood ratio chi-square, both of which indicate a very significant outcome because they are both less than 0.05, our alpha value. That being said, we reject the null hypothesis because when the p is low, the null must go. And the null is the outcome is independent of hospital. In other words, in our case, the outcome is not independent of hospital because we have to reject the null hypothesis given the low p-values. So, which hospital is different? Or which hospitals are different? Looking at hospital C, we notice that the values are quite different, higher chi-square values than the other hospitals. Also, in C, the full recovery is actually 76, the expected 60, so it's more than the expected. And the deaths for C are much lower, 5 actual deaths compared to expected 13 deaths. In contrast, Hospital D has more deaths than expected, so does Hospital A. And Hospital B is about expected. So chances are the hospital is different is Hospital C. Let's test that theory. We can do this by running another chi-square tables test, but exclude C. So if the result is they're all independent among A, B, and D, then we know that C is the one that is different from the rest. Let's do that now. Go up to Stat, Tables, chi-square test for association. And now let's select A, B, and D and leave out C. And click OK. And the p-value from the chi-square test is a very high 0.252 from the Pearson chi-square or the other chi-square tests. Regardless, both are high, higher than 0.05. Therefore, we fail to reject the null hypothesis. Practical conclusion, no difference among the 3 hospitals as far as outcomes go. So now we know that the one that's different is Hospital C. So, bottom line, send grandma to the best hospital in town, Hospital C. What happens if you want to test theories on differences in means using t-tests and ANOVA, but the data is non-normal? Well, those tests cannot be used. So what can you do? Fortunately, there's an alternative. You can compare medians instead of means using non-parametric methods. They can also be used if you want to compare medians because you're dealing with duration data like processing times. Let's go over some of the options for non-parametric methods. First, there's the one-sample Wilcoxon test, which can be used to compare the population median to a target. There's also the Mann-Whitney test, which can be used to compare 2 population medians of 2 groups. And there's the Kruskal-Wallis test that can be used to compare population medians of multiple groups. Let's apply these non-parametric methods using Minitab. To get started, download from the exercise files mediansdata.mtw and open the file. Here we have three groups A, B, and C with continuous data. Let's assume you want to run t-tests. So, check for normality first. To do that, go up to Graph, Probability Plot, and select Multiple because we have multiple columns. And choose the three columns, A, B, and C, and click OK. Here we have the plots and the Anderson-Darling test together with the p-values. In normality test, a high p-value means data is normal because the null hypothesis is data is normal. In this case, we can see from the p-values that the only normal one is group A. B and C have very low p-values, less than 0.05, so they are non-normal. Given that, we cannot run a t-test. So what do? The alternate is non-parametric tests by comparing medians. So if you're interested in running a one-sample test against a target median, we can do that with a one-sample Wilcoxon test. Go up to Stat, Non-Parametrics, and we have the one-sample Wilcoxon. Our three groups, we want to test against a test median of, let's say, 70 as an example. Are they equal to 70 or not, as far as the medians go? Click OK. And we have the result, Wilcoxon test with the p-values. When the p is low, the null must go. So we can see that B and C have low p-values below 0.05. Therefore, we reject the null for B and C, but not for A. So A's median can be said to be equal to 70, whereas those of B and C are not equal to 70. So this is the one-sample Wilcoxon test. What if we are interested in comparing two groups, A versus B? Since we know they're not normal for one of them, we have to do the non-parametric test instead of the t-test. In this case, it will be the Mann-Whitney test to compare the medians of A versus B. To do that, go up to Stat, where the menu is, and drill down to Non-Parametrics, and choose Mann-Whitney test. We have two samples, sample 1 and sample 2, A versus B. And our alternate could be not equal to, greater than or less than, but of interest to us is not equal to. Confidence level, 95, and click OK. And here we have the Mann-Whitney test with the p-value at 0.07, still higher than 0.05, therefore we fail to reject the null hypothesis. So A and B medians are not different. If you notice, the confidence interval on the difference crosses the 0 mark, which means it's not different from 0. So there you have it, the two-sample medians test using the Mann-Whitney test. What if you're interested in comparing three groups, A, B, and C? We cannot use ANOVA because the data is not normal, so we use non-parametrics. And the test we use will be the Kruskal-Wallis test. To run that test, go up to Stat, Non-Parametrics, and select the Kruskal-Wallis test. Now, given that this dialog box requires a response and a factor, that means that it requires the data to be set in two columns, the actual data and the subscripts. So we have to stack the data. Let me show you how to do just that. Go up to Data and choose Stack, Stack Columns. Stack those three columns into two columns, essentially. We have a choice here. We can do it in a new worksheet or put it in the current worksheet. In the current worksheet, specify the columns you want. Let's say C5 for the actual data, and the identifying subscript, as far as whether it's A, B, or C, we can choose C6 and click OK. So here we have it, C5 and C6. C5, let's call it data for lack of a better term, and let's call this group. So if you scroll down, you can see you have group A, group B, and group C. They're all in one column. Essentially, what stacking does is to stack the 3 columns into one column with an identifying column next to it. So let's go back to our Kruskal-Wallis test. Go up to the Stat menu, Non-Parametrics, Kruskal-Wallis. The response is in data, and the factor or the identifier would be the group. With that, click OK. And you have the Kruskal-Wallis test with the p-value of 0.001, which is less than 0.05, our preset alpha value. Therefore, we reject the null hypothesis. The null hypothesis is all medians are equal. The alternate is at least one is different. So the conclusion is at least one of the medians is different. From earlier investigations, we saw that it was A that was quite different from the rest. So there you have it, an alternative to the ANOVA test. Have you ever wondered if the amount of coffee consumed on the morning of a test affects the outcome of your test score? Or is there a relationship between the price of apples and the price of gas? What I'm really asking is there a correlation? In Six Sigma projects, we're interested in seeing and analyzing how potential X's impact Y. Is there a relationship between X and Y? And if there is it a statistically significant relationship? That's when a correlation hypothesis test is needed. In Greenbelt training, you learn that when there is a relationship between two variables, we say there is correlation. The strength of the relationship is quantified by the correlation coefficient, or Pearson correlation coefficient. It can range from -1 to +1. And if there is no correlation, the coefficient is 0 or close to 0. The correlation and the coefficient are positive if one variable increases as the other increases, with a maximum positive correlation of +1. And the coefficient is negative if one variable decreases as the other increases. The maximum possible is a negative correlation of -1. When running a hypothesis test for correlation, the null hypothesis is there is no significant correlation. And the alternate hypothesis is there is significant correlation. The p-value in a correlation hypothesis test provides us with the ability to say whether the correlation is significant or not. If p-value does not exceed alpha, reject the null hypothesis. Conclusion: there is significant correlation. Now let's use Minitab to illustrate this with some examples. To get started, download from the exercise files correlation on apples.mtw and open it. Here we have 2 columns, apples and gas. We want to test theory that the price of apples is related to the price of gas. So always plot the data first. So to do that, let's plot a scatter plot. Go up to Graph, Scatter Plot, and we have a simple scatter plot here. Click OK. And the Y variable is apples. Assuming that gas prices affects apples, put gas in the X variable and click OK. And here you have it. I don't see any relationship here based on the shotgun scatter. Nevertheless, we can run a correlation analysis on this. To do that, go up to Stat, Basic Stats, and choose Correlation. Choose those 2, apples and gas, because that's of interest to us. Are they correlated or not? So let's click OK. And you have it. A correlation coefficient of minus 0.119. It's very small, very close to 0. Is it significant? No, it's not. How do I know that? By looking at the p-value. The p-value is higher than 0.05 of alpha. Here we have it at 0.580. Therefore, we fail to reject the null hypothesis. The null hypothesis in a correlation test is there is no correlation. And the alternate is there is significant correlation. With a high p-value of 0.580, we fail to reject the null. Therefore, there is no significant correlation. There you have it, correlation. In your black belt project, once the correlation is determined to be significant, the next question is, what is the exact form of the relationship? Or what is the regression equation? You may ask, Why the term regression? It's historical, and the term can be attributed to Victorian statistician Sir Francis Galton, who first used it to express how, as more and more data is collected, the values tend to get closer or regress toward the mean. And those means represent the line of best fit, which is termed the regression equation. More specifically, what is the y equals f of x? Once that is known, x's can be controlled to achieve the desired level of y. For instance, is there any relationship between the speed of a car and the stopping distance when brakes are applied? Let's use Minitab to look at some examples on regression. To get started, go up to your exercise files and download regression-data.mtw and open that file. Here we have in column 1, speed, and in column 3, stopping distance. Of interest to us is whether speed affects stopping distance. So speed would be the x, and stopping distance would be the y. So let's do a fitted line plot. Go up to the Stat menu, select regression, fitted line plot. Response is the stopping distance. Predictor is the speed. As far as regression models go, choose the simplest one first, linear. The rule of thumb is the simpler, the better. Here we have the fitted line plot. Looks very similar to a scatter plot with the blue dots, with the addition of the line. The line is the line of best fit or fitted line. The equation of that line is up here as shown. On the right, you can see the R-square values. At 98%, that's very good news. That means that 98% of the variation that we see in the data is explained by the equation. Let's go to the session window and see more details. We have the equation, the R-square, and the ANOVA table, showing a very significant p-value of 0.000, which is less than 0.05. Therefore, we reject the null hypothesis, because when the p is low, the null must go. And the null hypothesis in regression is there is no significant relationship. So the conclusion would be there is a significant relationship as seen by the fitted line earlier. Is the model valid? To do that, we check for residuals. The residuals are the error term in this equation up here. So if there are true errors, then they should be random and normally distributed. Let's check for that. To do that, we go to residual plots. We can get the previous dialog box by simply pressing Ctrl-E. Here we have the previous dialog. As for graphs, 4-in-1 residual plots. While we're here, let's ask for options and get some prediction and confidence intervals. OK, and OK. Residual plots. As you can see, it looks like the residuals or the error term is normal and random. That's very good news. So we have a valid model. Next, you have the prediction intervals and the confidence intervals. The wider band is the prediction interval, and the narrower band are the confidence intervals. The confidence interval band is simply a series of confidence intervals for the population means across the range of data. The prediction interval, the wider one, and that indicates the likely range of values for new observations. At any point on the regression line, for any given speed, you can be 95% confident that the actual stopping distance will end up within that vertical prediction interval at that particular speed. So for example, at 70, your stopping distance will be somewhere between the prediction lines. So because you've established the regression equation y equals f of x, as shown up here, you are now able to predict the y, or stopping distance, based on different speeds, the x. And now you know what the speed should be in order to obtain the desired stopping distance. Maybe you're wondering how a vehicle's speed and driver reaction time affect stopping distance. Or maybe you're curious if there is a relationship between height and weight and how gender might affect it. These are questions where there are multiple variables or axes that possibly affect an outcome or response, y. Multiple regressions need to be run to analyze these possible relationships and develop a valid model to predict future performance. Let's get started on multiple regression using Minitab. To get started, download from the exercise files the worksheet multiple regression data.mtw and open it. Let's deal with the first three columns first. We have the y being the stopping distance, and the potential axis would be the speed and driver reaction time. Let's do a regression. Go up to Stat menu, Regression, Regression, and Fit Regression Model. The response is stopping distance, and the predictors are speed and driver reaction time, both of which are continuous. We do not have any categorical predictor X right now. Go to Graphs and ask for 4-in-1 residual plots to check for validity, and click OK. It looks like the residuals or errors are normally distributed and random. That's good news. And in the session window, we have the regression. P-value of 0.000 means you have a significant relationship, and the axis, speed, and driver reaction times are both significant. So that's good. And we have an excellent R-square value here, where 99% of the variation in the data is explained by the regression line. Here we have the coefficients for speed, reaction time, and a constant term. The VIF here indicate that they are not too correlated. Anything less than 5 is good. And here we have the y equals f of x relationship. Minitab has a nice feature for predicting, whereby you can key in values for speed and reaction time, and it will calculate stopping distance, or the y, for you. To use that feature, go up to Stat, Regression, select Regression again, and select Predict. Here you have the response. We can key in a speed of 60, let's say, reaction time of 3 seconds, and we can key multiple values if you like. Click OK, and you have the predicted stopping distance of 249.878, and the intervals for that's predicted is between 238 and 260 will be the stopping distance. It's a very nice feature in Minitab. Now, what if we have categorical variables involved, or axes that are categorical? Go back to our worksheet. We can do Window, view the worksheet. In columns 5, 6, and 7, we have height, weight, and gender. And the theory is height and gender impacts weight. So let's do a regression on that, where weight is the y. To do that, go up to the Stat menu, Regression, Regression, and select Fit Regression Model. Change this to weight for the response. Select height for continuous predictor. And for the next one, categorical predictor, we'll select gender. Do the residual plots again, 4-in-1, that's good. And click OK. The plot looks good, normal and random. Let's go to the session window next. Here we have the regression, and essentially it is significant with a low p-value of less than 0.05. Therefore, the regression relationship is significant. And the axis, height, and gender are significant. And the good news is that the lack of fit is not significant. If it was, that means our model is not a good model. So we want something higher than 0.05. That is your alpha preset value. So this is good news to have a lack of fit that is not significant. Our R-square value is 89%, which means that 89% of the data is predicted by the equation. And where is that equation? Over here, 1 for each gender, for females and for males. So if you're a female, you use this equation, and for male, use that equation. Here we have the VIF values. VIF stands for Variance Inflation Factor. Essentially, a VIF close to 1 means that there is hardly any correlation between the terms. So that's good news. You want a VIF less than 5. So we are good there. So here we have the y equals f of x for height and weight for each gender. There you are, multiple regression. Now that you know which key axes drive the performance of y, you will want to develop and implement solutions to address the key axes in order to improve y. You're now in the improve phase. Remember, the main steps are: first, generate potential solutions to address proven key axes. Next, evaluate solution alternatives, then select the right set of solutions to optimize Y. Last, pilot and implement. Now, before implementing any solutions, you must apply these tools and techniques. New process maps to achieve a common understanding of the improved process. FMEA, or Failure Modes and Effects Analysis, to mitigate any potential risk of failure in the improved process. Also, mistake proofing to prevent any possibility of errors. And pilot testing to make sure it works before full implementation. Various tools such as DOE and process simulation may be used to determine optimal settings. Check out my course, Six Sigma Green Belt Training, for an introduction to DOE. Here in this Black Belt training, you'll have the opportunity to design and run experiments using Minitab. I cover screening experiments using fractional factorial designs, setting up and running full experiments using 2K full factorial designs, and optimization using response surface methods. As a black belt, you should be able to determine the best levels or settings for the key axis to optimize the performance of Y. And let's not forget the organizational side. On a change management note, it's critical that key stakeholders are involved and engaged during the improve phase. Key stakeholders include process owners, process operators, managers, and others who are impacted by the problem. Their input and buy-in are very critical during this phase and throughout the project. The improve phase allows you to design solutions so process performance can be proactively controlled and optimized. What if you have many factors, let's say 5, and you're unsure of whether every one has a significant impact? How big should your experiment be? A full 2K factorial design for 5 factors will require 2 to the power of 5 or 32 treatment combinations. With 2 replicates, that translates to 64 runs. And if each run takes 30 minutes, that's 32 hours of experiments. You'll probably be fired before taking away 32 hours of production time. There must be a better way to do a quick screening to determine which factors are significant to the response and which are not. In fact, there is. It's called a screening experiment using a 2K fractional factorial design. Fractional factorial designs enable you to screen a large number of factors to quickly determine which are the most significant. You can then focus on those few factors in a follow-up experiment to optimize the response using full factorial designs or response surface methods. Fractional factorial designs have fewer runs compared to the same number of factors in a full factorial 2K design. For example, a full factorial for 5 factors, k equals 5, would require 2 to the power of 5, which equates to 32 runs. While a half fraction, which is 2 to the power of minus 1, is a 2 to the power of 5 minus 1 design, will require only 16 runs. A quarter fraction is a 2 to the power of 5 minus 2 design and requires 8 runs. And in general, a 2 to the power of k minus p design requires 2 to the power of k minus p runs. To reduce the number of runs, the concept of generating relation is used. Let me illustrate with an example. Suppose we have 4 factors, a, b, c, d. With a full factorial 2 to the power of 4 design, there are 16 runs. We want to run a half fraction, or 2 to the power of 4 minus 1 design, with only 8 runs. Basically, we're trying to run 4 factors on a 2 to the power of 3 factorial. You can get the design for the 2 to the power of 4 minus 1 fractional factorial by using the letters of the 2 to the power of 3 factorial. A equals A, B equals B, C equals C, and D equals ABC. D equals ABC is called the generating relation. Here is the table of contrasts for a 2 to the power of 3 factorial design. As you can see, D uses the column of the ABC interaction. The assumption here is that the ABC 3-way interaction effect is assumed to be negligible. we say that D is confounded or aliased with ABC because we cannot distinguish between the effects of D and ABC. In this example, the price we pay for fewer runs is that the main effects are aliased with the three-way interaction, such as D with ABC. Our main purpose is to screen the many factors and determine which few main effects are significant. Fractional factorial designs make it possible to screen many factors quickly by using fewer runs than full factorial designs. The few factors found to be significant can then be used in a follow-up experiment to optimize the response Y. After screening has been done to narrow down the list of key X factors, either during the analyze phase or from a screening experiment, a full factorial DOE allows you to model using those key X's to optimize Y. 2K full factorial designs provide the means to fully understand all the effects of the factors, from main effects to interactions. For example, to determine the effects of sleep, study time, and exam room temperature on test scores, a 2 to the power of 3 factorial design was conducted. Here are the settings for the three variables. The experiment was run twice, so we say that there were 2 replicates. Now, let's set up a DOE using Minitab. To get started, open up Minitab with a new worksheet. We have to create a worksheet for the DOE. To do that, go up to Stat menu, DOE. Since we're doing factorial designs, we'll choose factorial and create factorial design. We have 3 factors in our experiment, so select 3. We want a 2K full factorial design, so we select design and choose full factorial. We also want to have 2 replicates, so select 2. As for the factors, we want to have our 3 factors typed in here, sleep being the first one, so type in sleep. And it's numeric because we have 4 hours and 8 hours for our low and high values. Put that in. And study time is also numeric, and we have it from 2 hours as the low setting and the 6 hours as the high setting. And room temperature, also numeric from 65 degrees, low, and the high setting is 75 degrees. So those are our 3 factors and the low-high settings. Go to Options. Typically, we want to randomize the runs, but for this course, we will uncheck this so we can all follow along with the same worksheet. And let's press OK. So we have the worksheet created for us. If the runs are randomized, the run order and the standard order would not be the same. Since it's not randomized, we all have the same order, the 3 factors, and typically we would type in column 8, test scores or the results for the experiment as we do each run. In this example, the experiment was conducted and the results came in. We have a worksheet for that. So go to exercise files and download DOE sleep worksheet.mtw and open that. We have our 16 runs because we have 2 replicates, and this is the data together with the test scores. Now that we have the results, what do? We want to analyze the DOE. To do that, go up to the Stat menu, DOE, Factorial, and Analyze Factorial Design. Our test score is the response, and the terms we want are the terms for the study. And we want graphs, the 4-in-1 residual plots, and effects plots to show us which effects have bigger effects and which effects are significant. And OK. The residual plots look normal and random. That's good. The effects plot for Pareto will prioritize the biggest effect to the smallest effect. We have the Pareto chart. It shows in a prioritized way which effects are biggest. B is the biggest, and that's study time, followed by A, that is sleep, followed by C, which is temperature, and an AB interaction would be your sleep-study time interaction. The red line here is an indication of significance based on the alpha value of 0.05, which is our significance level that we set. Similarly, we have the normal plot, same principle, except that now the further away the dots are, the more significant and bigger the effect. So B and A have bigger effects than C. C is temperature, and the A-B interaction, of course, is much smaller than A and B in this case. So it confirms the other plot. Let's go to the session window. Make this bigger. And we have the ANOVA table showing a significant p-value for the model, and our linear terms are significant. Sleep is significant, so is study time. Temperature is significant because they're all below 0.05, our alpha level. Also for the interactions, the only one significant is sleep study time at 0.035. Notice also the F values. For example, the F value for study time is 607 compared to the F value for temperature. The larger the F value, relatively speaking, the more significant. So temperature has a small effect, relatively speaking, compared to study time. It's a nice indication. Also, the R-square value here is 95%. That's very good. That means that the model explains 95% of the variation in the data. And the VIF, variance inflation factor, is 1. That means there's no correlation between the terms. And the terms are all significant for the coefficients of sleep, study time, temperature, and sleep-study interaction based on the p-values, which confirms our ANOVA table. And the rest here are not significant. This is the model, y equals f of x. Now what we need to do is, there's a principle in DOE, it's called the principle of parsimony. Essentially, it's the KISS principle, keep it short and sweet. If the simpler model can get the work done, we want to keep it simple. So let's keep the significant terms and remove the terms that are not significant. From our list, we have sleep, study time, temperature, and sleep study time are the ones that are significant. Let's remove the other terms that are not significant. To do that, go up to your previous menu, do a Control-E, go to Terms, and let's remove ABC. BC is not significant, and study time and sleep is AB, so AC is not significant. So we have the significant ones here, and we run the model again. Residuals are still good, effects are still good, and let's look at the session window. And this is a much simpler y equals f of x. It's easier to compute, and our R-square is still very high at 95%. And the ANOVA confirms it, that you have the significant terms here, except for sleep study time is borderline insignificant, slightly more than 0.05. The good news is that the lack of fit is not significant, with a p-value higher than 0.05. Therefore, it's not significant, and that's the good news that we want. Lack of fit is not significant. That's very good. VIF is still good, and our y equals f of x is much simpler to compute and use. That being said, let's look at factorial plots next. To do that, go up to Stat menu, DOE, Factorial, Factorial Plots. We have the interaction plot, sleep study time, and we have the main effects plot. As you can see, study time has a very big vertical rise as you move from 2 hours to 6 hours. And the rise in test scores is from 62 all the way to 86. Whereas in temperature, when you move from low to high setting, the drop is negligible compared to study time. And this confirms what we saw in the ANOVA table and the F values earlier. Finally, let's look at the cube plot. To do that, go to Stat, DOE, Factorial, and select Cube Plot. Here, we want to look at the fitted means, which is the values based on the y equation, y equals fx. Here we have the results. And basically, we see that the highest test score is the combination where we have study time at 6, sleep at 8 hours, and temperature at 65. So that is the best combination for our sleep study in terms of maximizing test results. There you have it, DOE for 2K full factorial. In 2K factorial designs, the assumption is that the response y maps to a straight line equation between the low and high settings of the axis. We say that y equals f of x is a first order equation. Here is the form of a first order equation, showing the main effects and interaction. What if it's not a straight line and there is curvature? In that case, a first order model is inadequate and will not be valid. A second order or quadratic equation is required, where the y equals f of x is not a straight line or a flat surface. You can see it here. To evaluate whether the model has any significant quadratic components, we need to test for curvature. This is done by including center points when creating a 2K factorial design. Let's illustrate with this example. What if the CTQ requirement for paper is whiteness? In order to determine optimal settings, a pulp and paper manufacturer wants to study the effects of two variables, percent of bleach concentration and temperature, on the whiteness of the paper, whiteness being the response. So, a 2 to the power of 2 factorial design is selected. For this example, the selected low and high levels of the factors are in this table. If you suspect that there is curvature in the response, design the experiment with center points. To do this, create an experimental design with 1 replicate and 5 center points. The center points are the middle values of both variables, in this case, concentration at 4.75% and temperature at 157.5 degrees. Now, let's run this factorial design with center points using Minitab. To get started, open up Minitab with a clean worksheet. We need to create the worksheet for the DOE with the 2 factors, 1 replicate, and 5 center points. To do that, go up to the Stat menu, DOE, Factorial, Create Factorial Design. We have our 2 factors, and the design we want is one with 5 center points and 1 replicate, which means 2 to the power 2 is 4, 4 plus 5 is 9, so we should expect 9 runs. The factors are, type in concentration, and we have that at 3.75% and 5.75% for the high. And temperature is our second factor, is numeric also, 152.5 as the low setting and 162.5 for the high setting. Here we have it. Go to options. Typically, we would randomize runs in a real experiment, but to have consistent, easy follow along for this course, let's unrandomize it and click OK. Here we have the 9 runs in standard order, no results yet, but wait, we have the results of the experiment already created. So let's go up to the exercise files and download DOE curvature.mtw and open that file. You have the whiteness results in C7. To analyze this DOE, we have to go up to Stat, DOE, Factorial, Analyze Factorial Design. The response is whiteness. Our terms are already there. And one quick note, include center points in the model. That being said, let me just point out something real quick. In the worksheet, is that center points are indicated by a 0. And if you notice the values, 4.75 is in the middle of 3.75 and 5.75. And 157.5 degrees is between 152.5 and 162.5. Literally the center of the low and high values of all factors. And these are the results. Anyway, go back to OK. Graphs. As for the 4-in-1 residuals, for the effects, Pareto is good enough. OK and OK. You have the residual plots, look pretty decent, not the world's greatest, but normal enough. And then we have the session window. Let's make this bigger. with the details of the results. Here we see the ANOVA table with p-values that are very significant in the terms as well as the interactions between concentration and temperature. But more importantly, the last line here, we have curvature. Since we had center points, the DOE model tested for curvature, and the p-value is significant, less than 0.05. That means that there is curvature in the response. It's no longer a straight line between the low and high level settings. So let's look at the factorial plots. Go up to Stat menu, DOE, factorial plots. We have the terms there. Okay. Here we have the interaction plot where the center point is the dot that we see here. Based on the legend, is brown or red. And we see that it does not rest on the line. So there is curvature in the response. So the real response is between the low to the center to the high setting. Similarly for the other line, it's a curve. In the main effects, we see it much more clearly. The true response is from this dot, it connects the dots. That's a true response curve. As you can see, it's not a straight line, it's a curve in both cases. So there is curvature, it is significant from the ANOVA table. Therefore, the factorial design will fail us. We have to use a different model to model curvature. And that model is called response surface methods. Response surface methods, or RSM, are another class of designs, different from factorial designs. The big advantage that response surface methods have over factorial designs is that RSM is able to model curvature and second order or quadratic relationships. If there is significant curvature, the factorial designs are not adequate. You can use RSM designs when there is curvature. The theoretical basis for RSM is that the output Y is represented by a curved response surface. A second order or quadratic model is required, as shown here, where x1 and x2 are the factors of interest. The difference between a response surface equation and the equation for a factorial design is the addition of the squared or quadratic terms. These terms are added to model curvature in the response. There are many designs in RSM. Central Composite Design, CCD, is the most popular. In CCD, all factors have only two levels, and the center points and axial points are defined. The main effects and interactions are determined by cube points, which are comparable to corner points of a 2K experiment. The curvature is determined by center points, and the quadratic terms are determined by axial points. Let's do RSM using Minitab. To get started, open up Minitab with a clean worksheet, and we have to create the CCD model, RSM, with 1 replicate and 5 center points. So let's do that. Go up to the Stat menu, DOE, Response Surface, create Response Surface Design, Central Composite or CCD design, that's fine. We have 2 factors. Let's specify the design. Select Design. We go with the default, that's fine. And click OK. And for options, that's not randomized, so we can follow along in this course. And factors, we want to do concentration and temperature. And the low-high values are 3.75 for concentration and 5.75 for the high, and for temperature is 152.5 and 162.5. There we have it. And the values here define the cube points, low-high settings. Okay? And okay. Here we have the 13 runs for our design, and the -1 here indicates the 4 axial points, and here are the 5 center points. We run the experiment and fill in the results in column 7, but we have the results in a file called rsm.mtw, which you can download from the exercise files. So open that file, rsm.mtw, and we have the results in column 7. Next, let's analyze this design. To do that, go up to Stat, DOE, Response Surface, Analyze Response Surface Designs. The response is whiteness. The terms are all there. Notice up here we have full quadratic because we're dealing with curved surfaces, and the RSM model has a quadratic equation. For graphs, we want the 4-in-1 residual plots. And click OK. We have very nice normal and random data for the residuals or errors, as it should be. That's very good. Let's go to the session window. Make that bigger. We have the ANOVA table for the model. We have a lot of significant p-values here, less than 0.05. So the linear terms, which is concentration and temperature, are significant. The squared terms, which is concentration squared and temperature squared, they are significant too, as you can see here with the p-value. And the effects are quite comparable to those of the linear terms based on f values. And the two-way interaction, represented by concentration temperature interaction, is significant as well, as we can see here. The next section here, we have the error term, which is the lack of fit. That is a high p-value. That means that lack of fit is not significant, higher than 0.05, which is fantastic news for us. Means that the model is a good fit. And of course, you have the pure error. The R square is 95%, which means that this model can explain 95% of the variation in the data. That's very good news. VIF is good, very close to 1. No correlation between the terms. And here is our y equals f of x. Notice it's a quadratic equation. Concentration is the linear term, temperature linear term, and then you have concentration squared here, and temperature squared. And of course, you have the interaction, concentration times temperature. Let's see some plots. To do that, go up to Stat, DOE, Response Surface, Factorial Plots. The terms are there. Click OK. And you have the curved responses in the interaction, as well as for the main effects. That's the beauty of RSM. It can model the quadratic curve. Other plots we can do are, let's go up to Stat, DOE, Response Surface, Contour Plot. This is fine as a default. Let's take a look. And here you see the contour similar to the topography of a mountain range, right? The highest being above 90 for whiteness. And this is the highest part of the mountain, so to speak. Looking top down, you have concentration and temperature. So high temperature, low concentration gives you very good whiteness. Another plot we can do is the surface plot. To do that, go up to Stat, DOE, Response Surface, Surface Plot. Click OK with the default. You have the 3D surface, where whiteness is the vertical axis, and the two axes at the bottom are the concentration and temperature variables. You can see the curved surface. Very nice. To optimize in terms of what is the best temperature and concentration levels to get various levels of whiteness or to maximize whiteness, Minitab has a very nice feature called Response Optimizer. Let's do that. Go up to the Stat menu, DOE, Response Surface, Response Optimizer. We want to maximize whiteness, so select Maximize. Sometimes you have a target value on a hit, you can do target as well. But for our case, or minimize in some cases. But for our case, we want to maximize. Do the setup. Looks fine. Let's do it with the default level. Click OK. And we have the optimization plot, essentially showing you the values of the concentration and temperature and the value you get for your y being the whiteness. Automatically, Minitab computes for you the best level. Since you're trying to maximize here, the best value you can get is 94.5979% whiteness, based on the values of 3.87 for concentration and 161.28 for temperature. and this is the curve it's based on. We can move things around by either typing in the values or moving the lines. And you can see different levels of the whiteness based on how you vary the factors. It's a nice way to play around and do what-if analysis. Nice feature. So there you have it, RSM for curve responses. The control phase is the most critical phase in your DMAIC project. If it's not done right, all the improvement gains will evaporate after your project ends. Process owners and operators who perform processes daily are the ones who will determine how sustainable the improvements are. And that's why their buy-in and participation from the start and throughout the project is so critical. The main purpose of this phase is to establish controls, to control the key X factors and monitor the Y to ensure the improved performance is sustained on an ongoing basis. The project team does not need to babysit the improved process. Let's take a look at the steps in the control phase. First, develop a control plan for monitoring, controlling, and regulating performance. The control plan tells us when to leave the process alone and when to intervene and what action to take. The control plan should be designed for the process owners and operators who carry out the process routinely, day in and day out. The next step in the control phase is to work with process owners to update procedures that incorporate the controls and to develop and implement communication and training plans. Then, help the process owners implement the changes. You can also implement SPC control charts to support your control plan. Then, determine the improved process capability and sigma level. You can do a comparison of the pre-project baseline to the improved post-project performance. Once project improvement goals have been achieved, the finance team will validate the actual financial impact. Last, project completion is signed off by the project champion. Then, you can celebrate your success. Mission accomplished. The control phase is technically the easiest of the 5 phases, but organizationally, the most difficult. Once you and your team leave, the people inheriting your work need the right tools in place to sustain the new performance level. There are some important questions to consider in the control phase. First, how would operators and process owners know when to take action and when to leave the process alone? The answer is SPC charts. And the next question is, what should be monitored to make that control possible? The answer, select the correct control subject. Based on the data type of the control subject, SPC chart for variables or SPC chart for attributes are used. For example, processing times are variable and defect rates are attributes. In any process, what should be monitored and controlled are the Y, the key axis, and any relevant CTQs. For example, if Y is the comfort level and one CTQ is comfortable temperature, then temperature is the X that should be monitored and controlled. That means it has to be regulated to maintain a particular temperature or temperature range that is comfortable. So temperature is the control subject. Your next question is, what data type is that control subject? Is it continuous data, such as temperature or processing time? Or is it attributes that are discrete, such as the number of defective items or proportion of defects? For variables or continuous data, you have a choice. If it's individual data, then use the individual or eye chart. To get a more accurate picture of the process, take the mean of multiple data points from a subgroup that are processed under the same operating conditions. Then use an X-bar chart which plots means of subgroups. These subgroups are called rational subgroups because the only variation among the data points within a subgroup is due to random variation or common cause variation. To capture variation from subgroup to subgroup, the range or standard deviation can be plotted. The range chart is called the R chart, and the standard deviation is the S chart. Traditionally, The R chart was more popular than the S chart because it was difficult to calculate standard deviations manually. But with the help of calculators and computers today, that's not the case. Here are the most common SPC charts for variables. Individual or I charts plot individual values, for example, processing time of invoices. There's also the individual moving range or IMR chart, where along with individual values, the moving range of processing times are also charted. Next are X-bar charts, which plot the means of subgroups as data points. In addition to the X-bar chart, the range of each subgroup or X-bar R chart is plotted. And there is the X-bar S chart, which instead of ranges, standard deviations of the subgroups are plotted. Now, what if you want to control attributes that are discrete count or categorical data? For instance, should you monitor the number of errors in invoices? Or is it more important to track the number of errors per invoice? What about the number of invoices with errors? Or would it be more relevant to track the proportion of invoices that are erroneous? Based on what's important and relevant, you can select the appropriate SPC chart. So SPC charts for attributes are proportion or P charts, which plot the proportion of non-conforming or the proportion of defective units. For example, proportion or percent of invoices processed incorrectly. Next is the NP chart, where the number of non-conforming or number of defective units are plotted. For example, the number of invoices processed incorrectly. Another option is a C chart, which plots the number of defects. For example, the number of errors in invoices. And there is a U chart, which plots the number of defects per unit. For example, number of errors per invoice. Remember, there are two types of SPC charts: charts for variables and charts for attributes. Within each category, choosing the correct SPC chart is important because, as management guru Peter Drucker once said, what gets measured gets done. In Six Sigma Green Belt training, you were introduced to SPC charts in a number of videos. Now, let's talk about the use of Minitab for SPC charts. As a black belt, you will be expected to know how to develop and use SPC charts, and to guide others in using them. Knowing about SPC charts is not the same as having a hands-on experience in developing and analyzing SPC charts. With that in mind, let's practice this using Minitab. To get started, go to your exercise files and download spcdata.mtw and open it. Look at the column length, and essentially it's continuous data, individual values. So the chart to use would be the I chart or individuals chart. Let's plot that. Go up to Stat, Control Charts, choose Individual Chart, and plot length. Go to I chart options to specify what test you want to run. We want to test for all special causes. Okay. And OK. We have the control limits, UCL, lower control limits, LCL. X bar is the center line, the mean. And Minitab indicates that we have out of control points in these red dots, and the reference numbers are the test number that we failed at. So this process is out of control. For more detail, go to the session window. These are the detailed results of the out of control points. What if the data was attribute, pass, fail, for instance, such as we sample some parts in column 5 and got various rejects? In that case, because the sample sizes here are different, perhaps a proportion chart is appropriate. So let's plot that. Go up to Stat, Control Charts, Attribute Charts, Proportion Chart or P chart. We want to plot the results, which is rejects, and our different sample sizes are in subgroups, different sizes in sample. Go to the P chart options, and let's specify tests and run all tests for special causes. OK, and OK. Here you have the P chart. The uneven control limits is because of the different sample sizes. And is this process in control? No, it's not, because of the two out of control points. The details of that can be seen in the session window, 9 points in a row on the same side. So you have an out of control process. That's the P chart, attribute chart. What if I have a project which improved the processing time from 24 hours down to, let's say, 10 hours? The data is shown here in column 9. And I indicate the pre-project versus post-project by a column called phase in C10, indicated by 1 and 2. So how do I portray that improvement? To do that, we have to recalculate control limits for phase 1 versus phase 2. So let's do that with an SPC chart, in this case, individual chart. Go up to Stat, Control Charts, Individual Charts, select individuals, and now we plot process. To specify the various stages, go to the eye chart options, go to stages, and specify that stages is defined by our phase column. So when it switches from phase 1 to phase 2, it will recalculate the control limits. Here we go. Okay. And there you have it. Separate control limits for each phase. This is pre-project, high mean, and high variability. And the mean processing time is reduced drastically to 9.89 with a very consistent performance, less variance. So there we have it, a very good chart to showcase the success of your project to management. What if we did not recalculate the control limits? Then we have an erroneous SPC chart. Let me show you that. Go back to the previous menu by doing Control E. And eye chart options, we remove the stages. OK and OK. You have a SPC chart that is very misleading. Whenever you have a major change in the process, whether it's new equipment, new technology, or a big improvement through Six Sigma projects or quality projects, you have to recalculate the control limit to better reflect the random variation pre and post improvement. There you have it, SPC charts. Your project improvements have been implemented, and the process owners and operators are running the improved process under normal conditions. Now you want to confirm and display the improved process capability. Let's say your project was supposed to reduce the defect rate of products or transactions such as invoices, or maybe the project was supposed to reduce the mean and the variance of processing times. You need to know, did that occur? How much improvement was achieved? Did process capability improve? Did the Sigma level improve between pre-project and post-project performance? This will help you quantify the operational benefits and also help the finance team quantify the benefits in monetary terms. Also, showcasing improvements in process capability and operational and financial benefits is a great way to gain commitment and buy-in for future Six Sigma projects. So, whether it's discrete data such as defect rates or continuous data such as processing times, Minitab can help you display the improved process capability. Let's take a look at some examples in Minitab. To get started, go to the exercise files and download processcapability.mtw. Let's say we have data where we sample pass-fail data. We sampled 91 and found 23 defective units and additional samples, different numbers for that. What is the process capability for that process? To do that, go up to Stat, Quality Tools, Capability Analysis, and go to Binomial because we're dealing with pass-fail data. Defective 1, and our samples are in the column Sample 1. Click OK. Here we have the P chart. It looks like the process is very nicely in control. Nothing out of control here. Look at the summary stats. Percent defective is 21.19, corresponds to the center line here. the process Z at approximately 0.8 to get to sigma level at 1.5 gives us a sigma level of 1.5 plus 0.8 equals 2.3 sigma level. Post-project, we have the data in column C5 and C6. So perhaps in the control phase, let's determine the process capability. Using the same chart, we go back to the same dialog by pressing Ctrl E and key in the appropriate column, defectives 2 and sample 2. Okay. Here we have the process is still in control, but the numbers have dropped. Our percent defective is 4.63% and the process Z is 1.68. To convert to sigma level at 1.5, that gives us 3.18 sigma level. Nice big improvement from previously. What if our data is continuous data, such as processing times or delivery times? Let's say we have the data here in column C9 in the baseline measure phase and C10 in the control phase. And let's say the delivery time promised to customers is 24 hours or less. How capable is the process today compared to previously? Let's do the process capability chart. To do that, go up to Stat, Quality Tools, Capability 6-pack, go to Normal. The data is in delivery time 1. Since we're dealing with individual data points, the subgroup size is 1. Our upper spec is 24 because that's what we promised customers, 24 or less. Go to Options and ask for benchmark Z's for easy conversion to sigma level by adding 1.5. OK and OK. Here we have the eye chart showing that the process is in control, averaging 23.18 hours. And this is the histogram showing the percentage that's beyond 24-hour delivery. We have upset customers there. We have a CPK of 0.11 over here. Overall, our Z bench is 0.35 to convert to sigma level at 1.5. So our baseline sigma level is 1.85. With the improvements, let's see what the capability is. We can go back to the same dialog box by pressing Ctrl E and choosing the data column of delivery time 2. Click OK. And here we have the eye chart showing that the process is very well in control. No other control points there. Also notice the upper spec limit is at 24 and the process curve is way down here, averaging 18.9 hours delivery. And the spread is over here, nowhere close to 24. So very few, if any, that went beyond 24 hours. Not surprisingly, the ppm is at 0.09 parts per million. That's very good. Our Z bench is 5.21. To convert to sigma level, simply add 1.5 to that. That gives us 6.71 sigma level. Excellent performance. You can showcase the results to management, and it is a very successful project. Congratulations. Congratulations, you have made it to the end of your black belt training. With the knowledge gained from this course, you should have the confidence to lead and carry out Six Sigma black belt projects. You are now able to use statistical and advanced quality tools to analyze data and drive improvements. There are many resources available for black belt practitioners, including Minitab.com, which provides additional resources and guidance on analyzing data. Another is iSixSigma.com, which is a portal for Six Sigma practitioners to share ideas and best practices. And there are many professional associations you can join, such as the American Society for Quality at asq.org. I hope you've enjoyed this course. Good luck as you mentor yellow belts and green belts, and I wish you success in your black belt projects.